So one option that we see people do is the Uber shader, right? So it's basically this big, huge shader where they're using program flow control to basically see what, control what happens, right? So here we're saying, hey, maybe if I've got, this particular case, the graphics card's really awesome, whatever, do this super complicated material, okay, that's causing too much register pressure or something like that. So then I'm going to try the second material, it's not working so well, so on and so forth, until you finally, get to the material that's working for you. And you're going to do the same thing with a number of lights. Let's start off with 20 lights, like, not working so well, 19, so on and so forth, until you finally get to the lighting model that works for you. We also call this the one shader to rule them all model of coding. And there's some things that are, kind of good about this, I guess. All the functionality is in one place, kind of convenient. It reduces expensive state changes at runtime. That we definitely care about. One compile step, nice. And I don't know if this is really good or not, but we definitely notice a lot of people seem to do it. Okay, seems to be a popular coding method. What's bad is, of course, there's a reason that people like to write smaller functions that call other functions. This leads to very complex, unorganized shaders that are very hard to read. And probably more importantly is that register usage always winds up being worst case path through the code because the compiler doesn't know, right? The compiler says, hey, I don't know how you're going to execute through this code, so what I have to do is I have to allocate registers based on the biggest register hog in that whole code path. Okay, and register pressure is definitely something that affects performance, and so this is really bad. This is not what we want. Now another option is to do multiple specialized shaders for each combination of settings. Okay, so this is good because then you're going to use the shader function that you actually need, and you're going to get the optimal register usage for that function. It's easier to think about. When you're writing the code, it's easier to think about optimizations, right? Because like you're saying, okay, I have exactly this number of lights and exactly this material. And for the compiler, obviously, it's much easier for the compiler then to tease out those optimizations. So in two ways, it makes it easier to target optimizations for this kind of code. What's bad is that there's a huge number of resulting shaders, because now you've got this like n by m matrix of shaders that you need to write. So it's, this huge explosion in the number of shaders you have to do. It's still a lot, I think, to think about, and it's just a pain to manage at runtime, okay? There's definitely state change costs there. So what we've done is try and take the best of both worlds and introduce new constructs into the HLSL programming language that can be used to sort of get the best of both worlds. We want to get that better register usage while at the same time making code writing easier and cleaner. So in the runtime, what you're going to do is select the specific class instances you want. The runtime is going to inline those methods. Okay, so that's what gets you the good shader or good register usage. The inlining is done in native assembly, so it's nice and fast. And this applies to all subsequent draw calls, so you're less worried about state changes. So this is sort of the difference between the Uber shader code and the new dynamic subroutine code. And here what you're doing is you're binding the appropriate one at runtime. Okay, on to improved texture compression. So why do we need new texture formats in Direct3D 11? Well, a couple reasons. One, the texture compression that we use in Direct3D is what's called block compressed. Again, I think probably a lot of you know that already, but in case you don't, they're block compressed. So you take each block of the texture, you're going to compress it individually. And the interpolation models that we have for the existing BC formats, as they're called, are too simple. And so the problem is that the results, and you're going to see this in a couple of seconds, the results often have significant blocking artifacts. Okay, so that's really unattractive. We've all seen this. We also don't currently have high dynamic range support. And people really want this for bloom effects and other sort of complex lighting effects. These definitely are issues that we heard directly from developers, like, hey, fix this. We don't like it. It doesn't look good enough. So because of that, we have two new block compressed, or BCs, for Direct3D 11. The first one is called BC6. Sometimes it's also referred to as BC6H because it's the HDR compressed format, or high dynamic range, I should say, format. It offers fixed compression, 6:1 compression, going from 16 bits per channel. And it's targeting high but not lossless visual quality. None of the BCs are lossless. BC7 is the new improved standard dynamic range rendering format. It also supports alpha, so you're going to get 3:1 compression for RGB or 4:1 for RGBA, and this is targeting improved visual quality. So what stays unchanged, just to make it a little bit clearer, is each block is still compressed independently. That's what we want, because that's how the hardware can, just grab the pieces it needs and decompress those quickly and easily. And each block still has a fixed compression ratio. That doesn't change. But what does change is now the compression is tailored to the individual block content, right? So you can imagine that if you have one block that has a smooth color gradient, it's just going from white to pink, you can compress that in such a way as to get lots of fidelity along that gradient, really get that nice smooth gradient. Versus if you have a sort of very noisy image, right? Well, you don't need as much fidelity for each individual color, right? But you want to be able to represent that full space. And so the kind of interpolation you're going to use for those two different things is going to be very different. We also represent, I should say that compression, this new compression scheme, takes into account varied alpha versus constant alpha. So basically, we're just doing a better job of compressing different types of content because we're adding more complexity into that compression and decompression. Another big difference, and again, this gets back to this philosophy of we really want consistency, is the decompression results must be bit accurate with the spec. So this is something new, and people are very, very happy about this. So let's take a look at some example images now. So we have the original image here on the left, and we have the decompressed results using BC3, which is a fairly popular existing BC, and BC7. And what you should be able to see, and the projector's pretty good, I think you should be able to see it here, is that there's significantly more blocking artifacts with the BC3 image than there is in the BC7. And even if you can't see it in the decompressed image, you can definitely see it in the absolute error image, right? The BC7 just has a lower absolute error, so that's what's in the center. This is another example. These are normal maps. Again, the BC3 image, it just looks chunkier and blockier, and you can certainly see that in the absolute error image in the center. One last comparison, this is the HDR content displayed at a given exposure. So again, we have the original on the left and the decompressed BC6 at the right. There's nothing older for us to compare it to, so that's why you only get one comparison image. And here, what you should notice is when we look at the absolute error image in the center, it's just got this diffuse noise pattern. And that's exactly what we want. That's a good sign, because the human visual system has evolved to really notice blocks and lines and edges, okay? So when the error comes out as this kind of diffuse noise, it's much harder for us to see. And so again, this is what we want. This is good. Looks nice. All right. Now we're at the portion of the talk that I bet most of you are actually the most excited about. We're going to talk about the compute shader.